So now we can talk about precipitation reactions. You ever seen any stuff like this in your bathtub? I think that's a good reason to have white bathtubs or sinks, because then you can't see that as well. This is a hard water deposit. A bathtub ring is sometimes called because it goes all the way around the bathtub. So why does that form? Well, hard water has calcium and magnesium ions, and those react with soap to make this bathtub ring. It's a gray curd or a bathtub ring. Laundry detergents are different than soap. They have some things in them, like sodium carbonate, which will precipitate, will get rid of the calcium and the magnesium ions. Because if you use soap in your washing machine, you could end up with this gray soap scum stuff on your clothes. Yuck. So the sodium carbonate is very soluble. So here we have these carbonate ions, and when they encounter calcium ions in the water, they'll form calcium carbonate. Calcium carbonate is not soluble in water. Magnesium carbonate is not soluble in water. So it forms a solid, and it precipitates out of solution. When the meteorologists talk about precipitation, they're talking about things like snow, rain, hail, stuff coming down from the sky, right? So in the beaker, a precipitate looks like stuff coming down, like snow falling often. So a precipitation reaction is where you have a solid, known as a precipitate, that forms when you're mixing two solutions. So here we have a clear solution and another clear, colorless solution. Looks like we're mixing water with water, and as if by magic, we get this yellow solid forming. We can tell that this is a solid because it's not transparent. You can't see through it, right? Sometimes you mix two things and you get a clear yellow solution, right? But you can still see through it. Not being able to see through it, that it's cloudy, tells me there's tiny solid particles there. So here we have potassium iodide and lead nitrate solutions. And in those solutions, the ions are separate from each other. When we mix the two solutions, the lead ions encounter the iodide ions, and you can look this up in the table. Lead 2 with iodide, chloride, or bromide is not soluble. And so this forms a precipitate. It happens to be yellow, and it falls down. If you let this sit, eventually all the yellow stuff will settle to the bottom. The potassium and the nitrate ions are still there, but they don't form insoluble compounds with anything, so they remain soluble. So I think I've told you this, I think of the metals as being masculine and the nonmetals as being feminine. So here we have, I think of this as the guy potassium and the girl iodide, and they're hanging out together, right? And here we have lead and we have nitrate. Lead's the guy and nitrate's the girl, and they're hanging out together. And they're like, we're friends and stuff, but there's no like relationship or anything, right? There's no chemistry. So these guys go to a party. So they're going to the party in the Erlenmeyer flask, and they're going to mix together. And so they mix and they mingle and they go around, and lead hadn't met iodide before. And when lead meets iodide, he's like, wow, I really like this person. And she feels the same about him. There's this chemistry, this attraction that happens, right? And so they're just like, they spend the rest of the evening together. You can't separate them, right? In fact, if there's, this is the solid down here. Come on, Bodner. The solid down here. This is, they went and found a quiet spot, maybe that couch on the back porch, and they're just out there necking, right? They're just not part of the party anymore, right? That could happen, right? So lead and iodide getting it on the back porch, stuck together, very attracted to each other. What happens to potassium and nitrate? They're at the party. They're hanging out. nothing really happens to them. Okay? So our original solutions here, we had potassium and iodide. We have lead and nitrate. Lead and iodide did not form a solid because they're not that attracted to each other. We can look at the solubility rules, but I said lead. Potassium. Potassium and iodide. My brain's melting. Potassium and iodide. They are a soluble compound. They're like, yeah, we like each other enough to be a solid. When we're by ourselves, we just stick us some water, we'll go our ways and just mingle with everybody else. And then we've got lead and we've got nitrate. So, come on, pointer. Stupid thing. You mix these two solutions, and now you have to look at the possible interactions between these ions. Okay? So, these are dealing with positive and negative charges. So we can't have positive charges being attracted to each other. Physics says that can't happen. So we can't look at whether potassium and lead are going to get together. They have the same charge. They're repelled by each other. But we can look at, I want my pointer. I'm having connection issues. We can look at whether potassium is going to have a relationship with nitrate or lead with iodide. So what we're thinking here is we've got two couples coming to this party. They're just, casual with each other. And we're going to swap partners and see if magic happens, see if chemistry happens. If it does, we've got to precipitate. If it doesn't, it was just a bunch of people getting together and hanging out. Because you don't always get a precipitation reaction. Just like, you get a bunch of people together, you don't always have somebody, finding their soulmate, right? In fact, that's maybe kind of rare. So the precipitation happens only if we have some insoluble compounds. So if we've got potassium and iodide, sodium and chloride, those two couples come to the party and they mix and mingle. And potassium's like, oh, hi, chloride, just casual. And sodium's like, oh, hello, iodide, no big deal. They just mix. There's no chemical reaction because no insoluble substance formed. This isn't a chemical change. No, something has happened, right? These ions are now all mixed up together, but that's a physical change. They've just mixed. There hasn't been a new compound that has formed. Does that make sense? So writing equations for precipitation reactions. Now that we know those rules of solubility, we can actually predict what the products are when two solutions of ionic compounds come together. So these are the steps. You need to start with the formulas for the two reactants. And then below the equation, write the formulas of the products that could form from the reactants. Look at the solubility rules to decide if either of those products is insoluble. If they're both soluble, then there's no reaction. Just write no reaction. Or we sometimes even abbreviate that with NR. If the products are insoluble, then you need to write everything out. We need to specify solid for the insoluble, aqueous for the soluble, and balance the equation. So, examples. Write an equation for the precipitation reaction that occurs, if any, when ammonium chloride and iron 3 nitrate are mixed. So this is going to give us a review of nomenclature as well. So we have two ionic compounds here. We need the ion formulas with their charges. So here I've got ammonium chloride. So that's one of the reactants. So ammonium is NH4 with a positive 1 charge, and chloride is Cl minus. So how do I put those together to get a neutral compound? Well, their charges are equal and opposite, so it's just NH4 Cl. Is that soluble? Yeah, because all ammonium compounds are soluble. So I should indicate aqueous. plus the other compound is iron 3 nitrate. What's the charge on iron 3? 3. The Roman numeral is the charge. And nitrate is NO3 minus because you memorize it. So we look at the charges to tell us how to put these together. I need 3 nitrate ions to balance the charge on 1 iron. So this is Fe, and I need 3 nitrates. And that's also soluble. So those are the reactants. On an exam, you'll probably be given the formulas for the reactants. But we're practicing a little bit here. So to predict the products, you want to have these ions with their charges written below the formulas. Because what we're going to do is we're going to swap partners and see if chemistry happens. So iron and chloride, ammonium and nitrate. They came in guy, girl, they have to leave guy, girl, okay? It's the charges, right? So we'll put ammonium with nitrate. And just right there, I'm just copying the ion formulas over here with their new partners. So I can write a formula for ammonium nitrate. Is that going to be soluble or insoluble? It's going to be soluble because all ammonium compounds are soluble, right? What we're looking for here is something that's insoluble. And then I have iron 3 and chloride. You go down that list, and you get to chloride being a soluble compound, and the exceptions are lead, silver, and mercury. Thank you. Blanked out on that one. Iron is not an exception. This is also soluble. So what do? No reaction. And an R, no reaction. There is not a chemical reaction here. It's just mixing. It's always fun when that happens because it's a lot less work. Write an equation for the precipitation reaction that occurs, if any, when sodium hydroxide and copper 2 bromide are mixed. We're going to do the same thing. We have to look at the individual ions, so sodium hydroxide. Okay, sodium ion and hydroxide ion. If you haven't learned your ions yet, this would be a good time to get on that. Put those two together. I get NaOH. That's soluble. The other one is copper 2 bromide. So copper 2 is copper 2 plus. Bromide is Br minus. When I put those together, I need 2 bromides, and that's going to be aqueous as well. I'm leaving a little space here in case there's a reaction and I need to balance it. Now we're going to swap the partners and see what happens. We're going to put copper with hydroxide and sodium with bromide. It doesn't matter which pair you write first, but it's always the positive and then the negative. So let's put sodium here. Sodium with bromide and copper 2 with hydroxide. And then you go to the table of the solubility rules. At some point you need to have that table in your head. So we go down the list. Sodium compounds always soluble. So that's soluble. Here, copper, you're not going to find copper 2 on the list, but you're going to find hydroxide. I left off the charge. Hydroxide ion. That's in the bottom of the table. Usually insoluble, except calcium, magnesium, and strontium. Yeah, I think it was strontium. Those are slightly soluble, but it's not one of those. So this is an insoluble compound. This is going to form a precipitate. Copper and hydroxide are going to get it on. Do people still say that? I'm dating myself. So I need 2 hydroxides, and I'm going to put S here. That's the solid, that's the precipitate that forms. Sodium and bromide are still aqueous, just hanging out with each other. And then I need to balance the equation. Sometimes it's already balanced. Is it already balanced? No, that'd be too nice. If I look over here, I see I've got 2 bromides on the left side, and I've only got 1 over here. So I could fix that by putting a 2 in front of sodium bromide. That messed up the sodiums. Right? So 2 sodiums, well, I better go over and fix that. 2 sodiums. I've got 1 copper on each side and 2 hydroxides on each side. It's balanced. Any questions?